All right, so yesterday we did the kinematics review where I told you kind of the key points from kinematics. Those key points were going to be, scalars and vectors, position versus time, velocity versus time graphs, vector component addition, and projectile motion. All right, so just as a quick review here, okay, I'm just going to go over a few examples of those kinds of things, and then we'll move on to dynamics after that. Okay, so if, as an example, I had a position versus time graph that okay, let's say I had a position versus time graph that looked like this. Okay, so we got meters here and we've got seconds here. And I asked you to calculate for me the average velocity of the object. What would you need to do? Well, I can't calculate the slope because I don't have one single line. If this was one single line, the slope would tell me the velocity, yes. Okay, but in this case, because I don't have a single line, I'm going to need to use v equals d over t. Okay, that's what if I have a single line, then the slope is kind of v equals d over t. Okay, but we have to take into account the y-intercept, right? So what I need to do is figure out the total displacement, because average velocity is total displacement divided by total time. That's final position minus initial position divided by time. So my final position is -4 meters, okay? And my initial position was +5 meters. Everybody okay with that? Okay. And this whole thing takes 9 seconds. All right, so I've got -4 minus 5, okay? So that's going to be -9 divided by 9. What's my average velocity? -1 meter per second. Yes, because I didn't give you anything else, right? Watch, though, on a graph, if you got a graph that looks like this, or any graph for that matter, sometimes the label will be, it'll say something like this: position in meters north. Okay, so watch for abbreviations like that on an axis. Okay, it's not often that I do that, but it can come up occasionally. Then it would be 1 meter per second south, exactly. Right. Okay, what if, same graph, now I ask you calculate the total distance traveled. Yeah, 9 meters. Okay, because they don't go anywhere here. They go from +5 to -4. Okay, that's 9 meters, and then they don't go anywhere here, right? So they only go a total distance of 9 meters. Okay. All right. If I had a velocity versus time graph. I think we talked about this one yesterday, didn't we? I did this example, I think, but we'll just quickly review it. Okay. And I'm just making up numbers here, but let's say I have a velocity versus time graph, okay, that looks like this, and I ask you to calculate the total displacement to 20 seconds. Well, remember, direction doesn't matter for distance, right? I do have to take into account that it went below here when I'm calculating that it went 9 meters, right? But no, I don't put the negative on my answer. Okay, so if I'm looking at this one here and I want to calculate the total displacement, that means I need to calculate essentially the area under the line to 20 seconds, right? So I need to calculate this box, okay, and this triangle, right? Which I can do if I use D equals VI times T plus 1/2 AT squared, right? That calculates the area. Or I could actually go through all the motions of calculating what the height of this triangle was, okay, by calculating what's Y at 20 seconds, okay, subtracting the 1.72 from that and calculating the area going 1/2 base times height. That would also work, okay, but this is quicker, obviously, okay? So punch in my numbers and I've got my total displacement from there, okay? If the graph doesn't look like that, if the graph has a different shape, it's not a single line, maybe it goes like this, okay, then what do? Then I got to break it up, right? I got to find still the area underneath the line, but I've got to understand that, okay, I've got an area where we accelerate, so I use average velocity times time, half the base times height, okay? Average velocity times time, base times height, half the base times height, okay? And I'll get my total displacement.
Ever be one like that where it was like curved?
We didn't do a lab where we had a curved velocity time graph. We had a curved position versus time graph, but we never calculated anything from it. Yeah. All right, ringing a bell for graphing. Okay, so things like that. All right, and then vector component addition. So let's just maybe, I'll just make one up here. You guys can write it down and we'll just walk through all the steps together. Okay. Okay, so this would be about as complex as we would get because these ones track back on each other a bit. Okay. So we've got our two vectors. Okay, we want to draw them in what way? Tail to head, right? Okay, so we've got our first vector is north of east. So I'm going to draw. Oh, I should draw further up here. Okay. There's my reference line. That's east. I'm going 30 degrees north of that. Okay, for 5.6 kilometers. There's my X, there's my Y, okay, and then I've got 2.2 kilometers at 10 degrees south of west. Okay, so here's west, okay, 10 degrees south of that would be pretty thin. Okay, so this would be 2.2 kilometers, this would be 10 degrees, here's X, here's Y, okay, and then my resultant would go like this. And it would represent my total displacement. Okay, everybody all right with the diagram? Okay, scale and direction somewhat important here. Yeah, I mean, I picked numbers that were, we probably weren't going to mess up too badly because they were significantly smaller. Okay, but now we need to calculate all of our x's and all of our y's. Okay, so to calculate black x, okay, black x is adjacent to the 30-degree angle, so that's going to mean the cos of 30 degrees times the hypotenuse, which was 5.6 kilometers. All right, so we're looking at 4.8, well, 4.850, we'll say. I'm going to write 849 because I'll try and use as many decimals from that number as I can. Okay, kilometers, and that's east. Okay, the y component is the opposite side, so that'll be sine of 30 times 5.6, okay, which should be 2.8, yeah. 2.8 kilometers north. Okay, I have to do the same thing with the red triangle. Okay, red x is adjacent to the 10-degree angle, so cos of 10 degrees times 2.2, which is the hypotenuse. All right, so we're looking at 2.167. Red. 2.167 kilometers west. Okay, and y is going to be the sine of 10 degrees because it's the opposite side times 2.2. So it's going to be pretty small. All right, so 0.382 kilometers. Okay, and that'll be south. All right, so now I've got all my x's and all my y's. What do I do with them? Yeah, I add them up. I use them to get my resultants x and y. In this case, I'm actually not going to add, or I'm going to add them as negatives because they're all opposite. Okay, so to get green x, okay, I'm going to take my easterly component, which was 4.849, and add it to the other east-west component, which is negative 2.167. Okay. So 4.849742261 minus 2.166577. Okay, so we've got 2.683 kilometers, and that'll be east. Okay, for our green x, which seems about right given my scale. And then to find green y, I'm going to take the north and subtract the south since it's bigger. Okay, so we'll have our 2.8 minus 0.382. All right, so we're looking at 2.418 kilometers, and that is north. Okay, everybody with me so far? Okay, important to remember which directions are which. Okay, now I've got my resultants triangle figured out. So now I can calculate my resultants magnitude using Pythagorean theorem. Okay, so our magnitude of our displacement will be the square root of 2.863 squared, okay, plus 2.418 squared. Okay, so my resultant's 3.61 meters, or kilometers, sorry, 3.61 kilometers. Okay, that's its magnitude. Now I need to find its direction. Okay, I'm going to use the opposite and adjacent sides for that. So that's going to be tan to the minus 1 of the opposite side, which is x, 2.863, divided by y, 2.418. And that'll get me my angle. And of 0.683, not 863. Oh, yeah, 683. Whoop. Divided by. Okay, so I'm looking at 48.0 degrees. And for me, that angle is east of north. Okay, but obviously 42 degrees north of east would also be an acceptable vector as it's the complementary one. Okay, and I think we had, did we only have 2 significant figures in that question? We did, so it should actually be 3.6 kilometers at 48 degrees east of north. Okay, so my reference direction is my second direction. I went east of, so whatever one the angle arc touches is your second one. Okay, east of north. Right? If I drew the triangle this way, then my angle arc would be here, and this would be north of east. Yeah. All right. Is that ringing a bell for everybody? No? Yeah, I probably wouldn't give you one that complex on a final exam. Probably, you know, like flat one and an angled one, right? Just like you got on your unit exam, just for the sake of expediency. I just need to know, can you still do vector component addition, not how fast can you do vector component addition, right? All right, and we did say that this is one that could very likely be part of a dynamics question in terms of a vector sum of all forces, net force kind of situation, because that's an easy way for me to shorten the test a bit by combining those two concepts. All right, and then projectile motion, right? Because I did tell you that the first question in the written response was a projectile motion question. So I'll go over one that's projected horizontally and one that's projected at an angle, and so you see both. Yeah. Okay. All right, so let's do a horizontal one first. Okay, so I've got a cliff, right? I've got something rolling off or running off or whatever off the cliff at 10 meters per second. Okay, and the cliff is, so this will be my vertical information. We'll say the cliff's 120 meters tall. Okay, we want to calculate how far from the base of the cliff the object will land given that information. Okay, so we break it up into vertical and horizontal components, okay? I'm looking for the horizontal distance. I have the horizontal velocity. Okay, it's 10 meters per second. Vertically, I know the vertical distance or displacement is 120 meters. I know the acceleration is 9.81 meters per second squared. I don't have to make that negative here because it doesn't change direction. It's always down, so I can just use positive for down. Okay. What else do I know vertically? VI is 0. That's the most important thing I have to remember about anything projected horizontally. Thrown straight horizontal from a vertical perspective is no different than dropping something. Okay. The initial velocity vertically is 0. All right. If I'm going to find my horizontal displacement or distance, then I'm going to need what? I'm going to need time because we use v equals d over t for the horizontal stuff. Can I find time with this information? Yes, I'm going to have to use this formula. D equals vi times t plus 1/2 at squared. Since that's 0, okay, I can eliminate it, which eliminates one of the times, which is nice. Okay, and now I just need to solve for t. So I'm going to get t by itself by dividing both sides by half of a and square rooting it, right? All right, so that'll be 120 meters divided by 4.509. Okay, half of 9.81. Okay. All right, so we're looking at a flight time here of 5.158 seconds. Okay, that is the only thing that the horizontal and vertical components share. That's true for either type of projectile motion. All right, so now I can calculate d by going v times t. So 10 times the 5.158, okay, will give me 52 meters. To two significant figures. Sorry, 4.905. What am I doing? 509. You're right. Okay, so I got the wrong number here, and thus the wrong number over here. Feeling a little bit dyslexic today. I've done that. I did that in my Science 10 class twice too, where I reversed something. Okay, 4.905. There we go, 4.946. Now we multiply that by 10, and we got 49 point, well, just 49, because there's only two significant figures here. Okay, so that's projected horizontally. There's only three ways I can ask you a projected horizontally question. Ask you to find the horizontal distance, ask you to find the height of the cliff, or ask you to find the horizontal speed. Okay, they all end up using the same steps, just in a different order. All right, and then the other kind would be something like this. All right, so I have an object that's moving, or that's being fired at 120 meters per second, 40 degrees above the horizontal, and I want to know how far horizontally will it travel and maximum height. Okay, so obviously, okay, in a question like this, I would also state, or if I don't state it, you assume it, that the initial height and the final height are the same, okay? If it's not stated otherwise, okay, I can't remember if I stated specifically anything like that on the final exam, but the picture will make it pretty clear, okay? Because there's a picture along with this one. Okay, so I need to break this up into horizontal and vertical components. So vertical here, horizontal over here. All right, first step, okay, find the vector components of this projected velocity. This is VI, this is V horizontal. All right, so to calculate VI, it's the opposite side, sine of 40 times 120. 77.135 meters per second, and that's positive. Okay, horizontally, it's the adjacent side, so we'll go cos of 40 degrees times 120. All right, so 91.925 meters per second. All right, now the other things I need to write down that I know. What's the acceleration? 9.81 meters per second squared. And obviously that only goes with the vertical part, and it has to be negative because it is going to change direction here. It starts going up and it ends going down. What speed, or velocity, sorry, does it end at? The same but negative as the initial, so negative 77.135 meters per second. That's for the entire flight, right? And that's what we need if we're going to calculate the horizontal distance traveled. All right, if I'm going to find the horizontal distance, I need speed, which I have, and time, which I don't. Can I find time with my vertical information? Yes. Okay, so I plug in here, T equals VF minus VI over A, right? Just our Science 10 acceleration formula. So we got negative 77.135 minus 77.135 divided by negative 9.81 meters per second squared. Okay, so 1316 times 2 divided by 9.81. All right, so we're looking at a time here of 15.73 seconds. All right, now I can put that over here and calculate my horizontal distance. 91.925 times 15.73. Right, but again, I want to use all my decimals, so 91.9253317. All right, so horizontally, it's going to travel 1.4 times 10 to the 3 meters. Okay, so like I was saying the other day, right, a projectile motion question makes you do everything from unit 1 except graphing. Okay, it makes you find vector components. It makes you do an acceleration problem. It makes you do a v equals d over t problem. It makes you remember your significant digits. Okay, all of that kind of stuff. Now, the second part of this question would be calculating the maximum height that the object will reach. That occurs here. Okay, so our vertical displacement at that point is the maximum height. What do I have to remember at this point?
It's not accelerating the speed.
Actually, it's still accelerating, but the velocity at this point is 0 because that's where it's slowed down, stops instantaneously before actually beginning to fall back. Okay, so VF equals 0 meters per second, or that the time I calculated is 1/2 of its value. You can do either way. Okay. So VF is 0 at that point, which means I'm going to use VF squared equals VI squared plus 2AD. Okay, and I'm going to manipulate for D here. So that'll be VF squared minus VI squared divided by 2A. Okay, so 0 squared minus 77.135 squared divided by 19.62. Okay, so 77.13451316 squared, okay, divided by 19.62. So the maximum height of this object will be 3.0 times 10 to the 2 meters. Okay, any other questions on kinematics? No? Okay. Okay, Newton's laws and work energy theorem are the big concepts in Unit 2. Okay, the biggest of Newton's laws is Newton's second law. Right? Newton's first law doesn't have any problem solving to do with it because it doesn't have any formulas to do with it, because what's the net force when we're dealing with a Newton's first law situation? It's 0. Okay, it tells us what an object does in the absence of a net force. Okay, and what it tells us is the object will either stay at rest or continue traveling at a constant velocity. That's the key part because direction matters. Okay, constant velocity. Okay, until acted upon by an external unbalanced or net force. So that's Newton's first law. There could be some multiple choice about that. Okay, Newton's second law is where we got into most of the stuff that we did. Right. So remember that Newton's second law. I don't know why I scribbled that. Second law. Okay, says that F net equals mass times acceleration and the vector sum of all forces. Okay. What kind of diagram did we usually draw to start these off? A free body diagram, right? So we draw a picture that's got, forces coming out of it, showing which way they're going and how big they are. Okay. Then we often had to put those forces into a what kind of diagram? A vector diagram, right? We had to draw them tail to head. Okay, figure out their components or whatever. Okay, but that generally is how that would work. Right now, we dealt with an untold number of different situations in which Newton's second law applied. Okay, we dealt with simple things like a car slamming on its brakes. Okay, we went to inclined planes. We talked about pulleys and systems. We talked about static situations where the net force was actually zero, but a bunch of forces were acting on the object at the same time. Okay, they just all happened to cancel each other out. Okay, just all kinds of different situations. Now, I can't ask all of those on the final exam, but what's my favorite? Inclined planes. Thanks. All right, so inclined plane, probably one that I would, if I was thinking about what's Mr. Coderre going to ask, I would think that. Why would I think that? Because I'm Mr. Coderre and I know what I think. Okay, so I would imagine that that's probably something you might see. Okay, and as well as maybe a vector type question. But are there vectors involved in an inclined plane? Absolutely. Okay, so it's a way to combine a couple of things and shorten up the test a little bit. So let's look at an inclined plane problem. Everyone okay with that? Okay. In fact, let's do this. That way we can practice two things at the same time. Okay, we can look at a system and an inclined plane. All right, so I think that should still work. I want the acceleration of the 4 kilogram mass. Okay, I want to find the acceleration of the 4 kilogram mass. What do I need to remember about a system? Right, that all parts accelerate at the same rate. And when I'm calculating that acceleration, I have to use the mass of the system, not an individual mass. That's why I would word it the way I just worded it for you. I would say I want the acceleration of the 4 kilogram mass, because that will tell me who remembers that a system is always calculated using the entire mass of the system. All right, so our next step here is identify all the forces that are acting in this system and then calculate them. All right, so I will have force of gravity here. Okay, and what else? I'll have an F parallel and a force of friction. Likely, which way is the friction acting? Likely down. We might find out otherwise, but okay, because I just picked these numbers out of my head. Okay, I would say likely that friction is acting down, because in my mind, I see this going up the hill. Okay, well, it should be. I think barely, but it should be going up the hill. Right? We might find out otherwise when we start calculating the forces, but we'll see in a minute, right? Okay, so I can calculate this force pretty quickly. Okay, 4 times 9.81 is going to be 37 point, what is it, 37 point, oh, sorry, 39.24, 39.24 newtons. All right, so I've got that force. Then I've got to draw my little triangle that goes inside of all inclined planes. Okay, this angle here is 30 degrees. This side's F normal, but I won't need that for this question. This side's F parallel. This side's FG. Okay, so I can calculate FG right now. Okay, so that'll be all right, so that's 58.86, and then I'm gonna calculate F parallel here in just a second. So this side's 58.86. F parallel is the opposite side. So sine of 30 times 58.86. Right, gives me 29.43. Okay, so this is 29.43. This is 9.5. Okay, and that means that, yeah, we are going to be just barely moving. Oh, so I found the opposite side. This is the opposite side of this triangle. The force of gravity was the hypotenuse. So I just did trig, sine of 30, just 0.5. Yeah. Okay, so now I've got all those forces. Now I want to calculate the net force by doing the vector sum of all forces. So F net, okay, will be 39.24 plus negative 29.43 plus negative 9.5. So plus 9.5, okay, oh yeah, just barely, 39.24 minus our answer there. Okay, so we have a net force of 0.31 newtons is what happens when Coderre just picks numbers out of his head. Okay, so our net force is 0.31 newtons. All right, now I can calculate the acceleration of the system, and as a result, right, of both masses. But what am I going to have to add to the 4 kilogram mass's acceleration? The direction, because it asked about a specific part of the system. Okay, so A will equal 0.31, the net force, divided by the total mass, which is 10. So our acceleration will be 0.031 meters per second squared down, straight down, because it's the 4 kilogram mass, which is falling. Okay. No, in this case, it would have to be down. Okay. We would need an actual direction here. Down the ramp, or 30 degrees below the vertical, or something that implies not straight down. Yeah. Okay, we had that talk during the unit, because a few people did that. Okay, that ringing a bell? All right, so there, now you've seen a systems question and an inclined plane question, okay, combined. Let's maybe look at one that's more vector related, because we had one like this on our unit exam, right? We had a box being pulled, okay, by, I don't know, let's just say this is 150 newtons, 10 kilograms, mu is 0.48. I hope these numbers are going to work out. Yeah, that should work. Okay, we want to calculate the acceleration of the 10 kilogram box. Okay, and this is what we know. All right, so we've got the pulling force, which is angled, but the box is sliding along the table. Okay, it's not moving in the direction of the 150 Newton force. So that means I've got, what's this force? Fg. Okay, and it's 98.1 newtons. Okay. Nope, won't cancel. Well, I mean, eventually, yes, the net force vertically will cancel, but the normal force does not equal the force of gravity in this situation. For what reason? Because you're lifting with the 150 Newton force. Okay, remember that this 150 Newton force contains a horizontal component and a vertical component. Right, so Fn and Fv will add together to cancel Fg. Right, that's important because we're going to need Fn to calculate what force that I haven't drawn on here yet. Friction. Then the box lifts off the table, which I made sure it didn't because I kind of did the math in my head. Okay, because the sine of 20 times 150 should be less than 98.1 newtons. Yeah. Yeah. Okay, so now I've got my free body diagram done. I need to calculate some forces here so that I can put them on there. Okay, the first ones I want to calculate are F horizontal and FV, so I can get rid of the angled force and simplify my diagram a little bit. Okay, so F horizontal, okay, will be the cos of 20, okay, times 150 newtons, and that's 140.954. Okay, the force vertical is the opposite side, so that'll be the sine of 20 times 150. Okay, so 51.303. Okay, newtons. So now I don't need this anymore. Okay. So now I've got a box being subjected to vertical forces that will do what? Cancel, and horizontal forces that will likely not cancel. Okay, the chances that FF is equal to FH are negligible. Okay, all right. So that said, I still don't know what Fn is, and I need Fn to get FF. But we've already said Fn plus Fv plus Fg equals 0. I can use that to get Fn then, okay? Because I know that this number plus that number add up to 0. Okay, so basically that means that Fn equals Fg minus the force vertical. It would be the remaining force, okay, since they add up to 0. So 98.1 minus 51.3. Oh, I could have just done answer. All right, so my normal force is 46.796 newtons. Okay, that helps me get friction in what way? Mu times Fn. Okay, so this question also incorporates what we learned about the force of friction. Okay, so force of friction is mu times the normal force. Okay, and we know that mu is 0.48 times 46.796. So this box is going to fly, okay, along the table here because there's way more force forward than there is backwards. All right, so our force of friction is only 22.46 newtons. All right, that force, that force, that force all add up to 0. My vector sum of all forces is 140 minus this number. Everyone okay with that? Nine, 5, 3, 8, 9, 3, 1 minus my answer. All right, so my net force is 118.49 newtons. Okay, divide that by 10, and we're looking at 11.8. Actually, we only have two significant figures here, so 12 meters per second squared. To the right, along the table, forwards, towards friend, pulling, whatever. Okay, anything that implies it's going that way. Yeah, in just a minute. Yeah. All right, does that make sense to everybody? Everyone give us that one? Okay, because like I said, we had one like that on your assignment, your Newton assignment, and one like that on your unit exam as well. Okay. So that incorporates some vector addition, it incorporates friction, okay, all of that kind of stuff. All right, so a static question. Okay, would look like that, and I would only say find the tension in the rope. Okay, find the tension in rope A, even though it's the same as rope B, and I would have to give you this angle, 110 degrees. Okay, what do I have to recognize about this question? Okay, even before I get to that point, I have to recognize that the net force is 0. Okay, then I can say, okay, each rope is going to bear half of the weight of the sign or of the light or whatever this thing is. Okay, all right, so I'm going to calculate the force of gravity. Okay, it's going to be 588.6 newtons. Yeah, I try and pick numbers I remember. Okay, so 588.6, okay, is my force of gravity. Each one of these cables has a triangle that looks like this. It's not 110 degrees. Each cable is 55 degrees. All right, and this line here is half of this number, okay, for each cable. And since I was only asking about one cable, I only want half that number. Okay, so I take that 588.6 and I divide it by 2. Okay, so I get 294.3. And now I can calculate the tension in this cable using trigonometry. It's the hypotenuse and I have the adjacent side. So the cos of 55 degrees equals, okay, the adjacent side, which I have, divided by the hypotenuse. So to get the hypotenuse, which is the tension, okay, it'll be adjacent divided by the cos of 55 degrees. So this number divided by the cos of 55. So there's 513, actually there's only two significant figures, 5.1 times 10 to the 2 newtons worth of tension in the cable. Remember, I don't have to put a direction on that because it didn't ask me which way it was pulling. It asked me the tension, which is just how tight the rope is. Okay. All right, that's the Newton's second law stuff that we talked about. Now we also had work energy theorem stuff in this unit. It was the second most important concept in unit 2. Okay? If I'm doing work, what am I doing? Don't say work, I already said that. Okay? If I'm doing work, what am I doing?
Exerting force over a distance.
Okay, I could be exerting a force over a distance and I'm changing. All right, what kind of energy? Kinetic and potential. When I add those two together, it's called mechanical energy, right? Okay, so the work energy theorem says that work is a change in the mechanical energy of an object. Okay, so let's say that I am comparing the top of this ramp to the bottom of this ramp. Okay, at the bottom of this ramp, the object is moving at 1.5 meters per second, and it's at the bottom of the ramp. Okay. A little while later, it is up here at the top of the ramp, which is 6 meters higher than the bottom, and it's now moving at 5.2 meters per second. This is a pretty easy one. I want to find the amount of work done in order to make that happen. I should have given you one less number. Okay. But this is an easy one. Okay, so if work's a change in mechanical energy, okay, can I calculate the mechanical energy here? Can I calculate the mechanical energy at the top? What do we do with those two numbers? Subtract them. Guys, change in mechanical energy, okay? Work means energy final minus energy initial, right? That's how you calculate change in anything is final minus initial, right? Change in position, final minus initial, okay? So what I would have here would be 1/2 mvf squared plus mghf, okay, minus 1/2 mvi squared. I don't have any potential energy because I'm at the bottom, and that one's done. Okay, that's all I have to do is subtract those numbers. Okay, so I wouldn't give you one that easy. I would probably make it more like this. I would say that a force of Oh, I would have to give you the mass too. I didn't give you the mass. Mass is 20 kilograms. Okay. Force is, well, let's say 600 newtons. I don't know, I'm just picking numbers out of my head here. Okay. 600 newtons, and the plane, this side of the plane is 15 meters long. Calculate the height of the ramp. Okay, does this change from a theoretical standpoint anything that I wrote for the last version? No, it doesn't. Okay, I'm still looking at work being a change in mechanical energy, but now I have to do that. The force pushing this thing up the ramp is 600 newtons. Okay, that's what we were given there. So the force along this 15-meter length is 600 newtons. Okay, so that can help me to calculate the change in energy. What part of this am I looking for? Yeah, I'm looking for H final, right? The height of the ramp. So I've got to do some manipulating here. Okay, so I'm going to add mvi squared over here. So I'm going to have force times distance plus mv 1/2 mvi squared. Okay, and then I'm going to subtract the 1/2 mvf over. Okay, and then I'm going to divide by mg. So it's a lot like a law of conservation of energy problem, except I'm adding in that it wasn't conserved. There was this much difference, 600 newtons times 15 meters. What did we say the mass was, 60? 20. Okay, so now that I've got my numbers plugged in and my manipulation done, okay, I can just 600 times 15, all right? So I did 9,000 joules. I'm adding 9,000 joules worth of mechanical energy to this system, okay, in pushing the block up the ramp. Okay, I'm going to add to that the initial energy of the box, which was 0.5 times 20 times 1.5 squared. Okay, so there's the energy it will have at the top of the ramp. Everyone with me on that? Okay, so now I'm going to subtract how much of that energy is kinetic, because what I'm looking for is part of the potential energy. All right, so I'm going to subtract from that 0.5 times 20 times 5.2 squared. All right, so I've got 8,752.1 joules of potential energy at the top. If I divide that by 20 times 9.81, that will tell me the height of the ramp. Holy smoke, that's a steep ramp, because the height is way bigger than the length. I don't know how that person pushed it up that ramp, because it's angled at like 70 degrees or so, okay? But that's what happens when I pick numbers out of my head. Yeah. All right, so does that make sense for work energy theorem? I probably wouldn't give you one that complex on a final exam. It might be a little simpler, like maybe only one kind of energy is changing or something like that, but you have to be able to recognize a work energy theorem question. Force times distance equals a change in mechanical energy. Okay. Is it also possible you could get a conservation of energy question? Okay, like a roller coaster, just like you did in Science 10. Okay, so expect you could also see something like that. Maybe let's just quickly go through one. Ball rolls down a hill. Simple. Okay, so I don't know what the initial height is, but I know the initial speed is 2.5 meters per second, and I want to know how fast the ball is going here. when it is, I don't know, 12 meters above the bottom of the ramp. Sorry, and it's moving here at, let's see, at 16 meters per second. All right, so I want to know how high was it started from. Okay. So what do I know is the same here and here? No, the mechanical energy is the same there and there. Did it mention anything about any work being done? Did it mention friction being present? If it doesn't mention that stuff, then energy initial equals energy final. Okay, do I have kinetic energy at the beginning? I have potential energy at the beginning. Okay, m times g times h initial plus 1/2 mv initial squared. Do I have both at the end? Okay, m times g times h final plus 1/2 mv final squared. Somebody said I need the mass. Do I? Not in this case, I don't. I do if it's a work energy theorem question, but in this case I don't, because the only thing acting here is gravity, and it affects all things equally. All right, I am looking for the initial height. So I'm trying to get this by itself. So I'm going to subtract the 1/2 VI over and then divide by G. So HI will equal GHF plus 1/2 VF squared divided by G. Okay, so 9.81 times 12 plus 0.5 times 16 squared. Oh, sorry, I forgot to subtract that over. You're right. I can still do that. Okay. Wow, can't believe I missed that. 1/2 VI squared. And all right. Okay, so minus 0.5 times 2.5 squared. Okay, so there's our initial potential energy. Divide that by 9.81. We're looking at 24.7 meters. Actually, we only have two significant figures, 25 meters. Okay. So is one like that going to be pretty straightforward? Okay. All right, any questions from you guys in regards to stuff from Unit 2? Anything else you want me to demo or explain? I think you guys chose some good questions on there. Okay, if you guys don't have any right now, hopefully some more will come up. Remember that I posted the exam review in Google Classroom yesterday. Okay, so if you go to the stream, you will find, okay, final exam review questions. Okay, so there's some old exam questions on there. Not many, there's like 5 or 6 from each unit. Okay, they have the answers there, so you can find out whether you did it right or not. Okay, they're a decent idea to try. The reason I don't have that many, guys, is because you've got tons of worksheets that have the problems with the answers on them. You got your assignments that have problems with answers on them. Okay, there's really no need for me to reinvent the wheel. Pick a few at random from there if you run out of ones on here. Okay, of course, if you do this sheet and you get every single one right on the first try, you're sitting pretty. Okay, in terms of what you know for the final. Okay, so I'll give you guys some time. Hopefully some more questions will come up, but if not, that's what you can work on for now. Mm-hmm.